In this video, we are going to talk mostly about lesson 13, which talks about more integer exponents. You guys already filled in this page 157. So this video is going to talk about these two definitions of exponents down at the bottom. We're going to talk about a base with an exponent of 0 and a base with a negative exponent. So let's get started. This is workbook page 181, problem number 1. Let me write that down for you. Hopefully you guys are listening though and you have your microphone on, or not your microphone on. I have my microphone on. Hopefully you guys have your headphones on and you can hear me. So again, this is workbook page 181. So you guys should be following along with me. So using this definition of base with an exponent of 0, any number raised to the 0 power is equal to 1. So here on workbook page 181, we're asked to circle all expressions that have a value of 1. So if any number raised to the power of 0 equals 1, then that means 6 raised to the power of 0 would equal 1, and you should circle this. So any single one of these that is raised to the 0 power equals 1, which means that would include this negative 6 raised to the power of 0 that also equals 1. Here we can simplify. We have 0 times 6 to the 0 power. So we can say that is equal to 0. 6 raised to the 0 power is equal to 1. So we have 0 times 1. What is 0 times 1? Well, that's 0. We are only supposed to circle expressions that have a value of 1. So we would not circle that one. I'm sure you guys, I'll let you guys figure this one out on your own. Should you be circling that one or not? 1 raised to the 0 power. And we can talk about this one. This is 6 raised to the 0 power divided by 6. Well, if I simplify that, the top, 6 raised to the 0 power, the numerator, that would be equal to 1. But there's nothing changing on the bottom. So this expression is actually equal to 1/6. So you would not circle that. Whereas this one, the whole number 1/6 is being raised to the 0 power. So that one would equal 1. Here you have the numerator 1 to the 0 power, which equals 1. And the denominator 6 to the 0 power, which equals 1. And of course, 1 over 1 is just equal to 1. So this entire expression does have a value of 1. Here you have to remember that this 6 is the coefficient. So this means 6 times x. I can rewrite that. 6 times x to the 0 power. Only the x is being raised to the 0 power. So that would be the same thing as saying 6 times 1. 6 times 1 does not equal 1. So we would not circle this one. Whereas this expression, this 0 power is distributed to both terms inside of the parentheses. So I could rewrite this as 6 to the 0 times x to the 0, which would equal 1 times whatever x is, which would again still be 1. Whatever x is, x to the 0 power is going to be 1. So this one we would circle. This entire expression does equal 1. So hopefully you've figured out that yes, you should be circling 1 to the 0 power, right? So these are the expressions that have a value of 1. All right, I'm going to skip a bunch of these slides And really, you're just going to start looking at the bottom of this workbook page. It's going to take me probably a minute to skip ahead to the slide that I want. So once this loads, you'll see that this is just the bottom of the same workbook page you've been working on. This is still workbook page 181. And as you can see now, we do have some negative exponents. So again, we're going to be looking here under our definitions of exponents, a base with a negative exponent. So these ones can get a little complex when we're simplifying these. And this is where I ended up getting a lot of questions after the Edpuzzle video that you guys watched on Friday. So this is saying for problems 2 through 5, use the definition of a negative exponent to write an equivalent expression with a positive exponent. We're always assuming that x is non-zero, which just means x does not equal 0. So for number 4, where it says x to the negative 8, we're just assuming that x is not 0. It can be 1, it can be 2, it could be like 0.5, whatever it is, it's just not 0. So all we're doing when we're rewriting these as positive exponents is we're putting 1 as our numerator, and then raised to, instead of the negative 7th power, it's 10 to the 7th power in the denominator. This you can think of as a fraction, you can think of this as a division problem, but essentially the way in which this works is that these two numbers um, 10 to the negative 7th and 1 over 10 to the 7th power, they are the, they have a relationship. They are the hello, I thought I was writing, but my Apple Pencil's being weird. They are multiplicative inverses of each other. So what that means is when we multiply these two numbers together, they are going to equal 1. So that's the way in which this works. 10 to the negative 7th power times 1 over 10 to the 7th power. If we multiplied those together, they equal 1, which is the definition of a multiplicative inverse. So all of these problems here, we are just rewriting so that they have positive exponents, which means we're putting whatever's being raised to that negative exponent in the denominator. So this would be equivalent to 1. Our 5 is negative, so we are keeping that negative, but now since we're putting this into the denominator, instead of having a negative 9, we have a positive 9. Try this one. Maybe pause the video so I'm not giving it away. And then try this one, number 5, on your own. Oh, actually, no, number 5 is a little different, so I'll do that one. I just didn't know if I'd be able to scroll up so you could see it. All right, so this is a little bit different. Again, this has a negative exponent, but here we see that in the denominator. So this one is going to be equivalent to 10 to the power of 2, 10 squared. It's kind of weird because everything is the opposite, right? In order to take away this negative and create a positive, we're going from it being in the denominator to it just being by itself. It's almost like you are, well, it's not almost like it, you are actually taking the inverse of this, you're taking the reciprocal, right? So if you're flipping this over, like we say keep, change, flip when we're dividing fractions, I'm talking about flipping this fraction. You're taking the reciprocal, right? So, sorry, this is weird. I'm trying to change the color here. Now I forgot how to do it. Change to green. So 10 over 2 is the reciprocal. It's really like has this imaginary 1, right? So you can see how I just took this, flipped it, and now I have from a negative exponent to a positive exponent. So all I did was really flip it. But because I don't have to write this denominator of 1, I can just write 10 squared. Okay. You can read, so he, but I'm going to skip that one for now. And let's take a look at problems 7 and 8, which are on the bottom of page 182. Oh, what did I do? Oh, not trying to look up anything on Israel. Page 180. Oh, goodness. Oh, goodness. Ah, no, I don't know what this is trying to do. All right. I'm not going to scroll up that much anymore. I don't know what I was doing here. Sorry about that, guys. So again, this is workbook page 182. That is all I was trying to write. All right. Problems 7 and 8. So again, we're going to apply the properties and definitions of exponents, which is that paper that we keep flipping back to, this workbook page 157. So we're going to apply the properties and definitions of exponents. To write an equivalent expression with only positive exponents, we are going to assume that D is not 0. Oh gosh, now things are really being wacky. So in your Edpuzzle, it probably talked about division of exponents essentially being subtraction. And just like we said earlier about this using the reciprocal and everything, all of that works, all of that is true, but just really a shortcut to doing that is to think of these as subtraction if we have the same base. So in number 7, we have 8 to the 13th power divided by 8 to the 21st power. Because we have the same base, we have an 8 and an 8, we can use subtraction of these exponents to end up simplifying this expression. I'm going to have to refresh this because it's being completely crazy. All right, hopefully this works well. So we can say this is the same thing as, I guess I'll show you as using kind of that reciprocal. This is the same thing as saying 8 to the 13th power times the reciprocal, like we're flipping and changing from division to multiplication, 8 to the negative 21. Because you know this property for product of a power with like bases, remember how when you have the same base, it's that very first description here up at the top. When you have the same base, this like bases, you have the same base, you can actually add the exponents. So that's the property that we will be applying here. So I can say this is equivalent to, now my calibration is off again on my Apple Pencil, 8, oh yeah, I can't do that. Let me refresh again. This Great Minds website has been acting so weird all day. All right, I'm going to do this without going back to another page. So hopefully we can get through this. Again, 8 to the 13th power times 8 to the negative 21st power. Since I know that I can apply the property for products with like bases, I can say this is the same thing as 13 plus a negative 21, or 13 minus 21, which is 8 to the negative 8. We are supposed to be rewriting this using positive exponents. So because this is a negative exponent, I have to put that in the denominator and make it positive. So on number 8, we're assuming D is not 0, but we're simplifying this a little bit more. I can think of this problem, I can split up. This is a division problem, 7D to the 4th power divided by 14 times D to the 7th power. So I can break this up. I can say that's the same thing as 7. Actually, I'll do it this way first. I'll write it all on the top, right? 7D to the 4th power is like saying 7 times D to the 4th power over 14 times D to the 7th power. And I can split that up into different fractions if it's easier to see. I know that 7 divided by 14 is equal to 1/2. So I can simplify that one right away. And then when I'm looking at my variable of the letter D with my exponents, I can use that subtraction. So I can say that is equivalent to times D to the 4th times, since this is in the denominator, I'm going to have to make this D to the negative 7th power. I can simplify this into D to the 4th plus a negative 7 . I'm trying to think which color I wanted to switch to, sorry. I'm like, oh, okay, so I still have that 1/2, that didn't change, but now I'm simplifying this part, so I have D raised to the 4 plus a negative 7. Well, 4 plus a negative 7 is negative 3. Again, I'm supposed to be writing only positive exponents. So this D to the negative 3rd power is going to have to go in the denominator. I already have a 2 in the denominator. So this D to the negative 3rd power is going to go into the denominator, just like my 2. My 1 is going to be the part that stays in the numerator. So even a very kind of simple looking problem like number 8 can start getting a little complex. My advice here, if you're watching this video, is to be writing down every single step so that you can go back and you can look at your notes on this rather than just skipping ahead and writing down the answer. Because these do get pretty complex. You really will have to think about these and practice these. I'm going to assign you some practice problems in Google Classroom to give you some practice working through some of these problems.